Okay. Hopefully this works. All right. Okay, so today I'm just going to do a quick review for exam 2. Um, I say quick, a more in-depth one than I did on Friday. So I'm going to do a little bit more example problems and working through them. And then this is obviously recorded and posted for anybody who needs access later. So let's crack into it. I'll check my screen. Okay. So starting from the top, example problem 1. So there's going to be 3 major questions in this exam. The first one's going to be about direct methods of solving systems of equations. Number 2 is going to be iterative methods for solving systems of equations. And number 3 is going to be iterative methods for solving nonlinear systems of equations. So example problem number 1. So you're given this linear system A, B, and then we give you the inverse of matrix A, because having to like find the inverse on your own would be actual dookie. So we're not going to do that to you. Here's an example 1. I made sure to keep it in fraction form. We will likely, so when we give you the inverse of A, it'll likely be in decimal form. So we'll give you like, the matrix, but instead of these pretty little fractions of sevenths and 21sts, whatever, you'll be given actual like decimals. So yeah, part 1 of question 1 is going to be, what's the conditioning number for coefficient matrix A? We might ask you, so like to kind of give you more of a hint, the way we might ask this question is to say, using the inverse provided here in the infinity norm and the infinity norm of inverse of A, the conditioning number is, or the conditioning number for coefficient matrix A is blank. So that will kind of clue you in that you need to find both the infinity norm of A and the infinity norm of the inverse of A. So by doing so, we all should know that finding the infinity norm for a matrix entails summing up each row of the matrix and then finding the largest component of the resultant vector. Whatever the largest component is, that is your infinity norm. 1 second. Sorry about that, got a phone call. Anyway, so in order to solve it, I worked out kind of step by step finding the infinity norm of A, which is shown up here. So you add up your 1, 1, and 1, and that should leave you with a 3. Add up 0, 2, 5, and that's 7, 2, 5, and -1. Uh-oh. Oh no, I think I've made a mistake. I always do this. It's always little numbers or little issues. So And then this should be 7. Okay, so our answer is 7. I know I did it right with this other one. But anyway, so the solution should be these two norms multiplied together. So 7 times 1.7142, which would be, pull out our handy dandy calculator here. Say 4, 3, we'll round that up times 7. And that answer is 12. Okay, so hopefully I didn't screw that up. Oh, I did screw it up. I was right the first time. Okay, totally ignore all of that because I forgot that you are supposed to take the absolute value of each component as you sum them up. Totally my bad. So yeah, no, this answer was right the first time. I had a mind blank because I got distracted by the phone call. Anyway, so yeah, that's our conditioning number. So the next question is going to ask you kind of something along the lines of like, hey, what does this conditioning number mean? And one of the things it means is that if it's small, it's a well-conditioned system. And if you yield a small residual, then your solution is going to be accurate with this system. When we say small, it's kind of like a relative thing. There's no hard limit to say like, hey, if your conditioning number is greater than 10, it's going to be big. That's not really how it is. When we say that a conditioning number is large, we mean like a big number. If it's anywhere like less than 100, you're probably safe to say that it's small. And we likely won't give you a number that would be, like a vague, is this big or is this small? Because like 13.7 is considered small. So do note that. Next, number 3, so using the same system, perform Gauss elimination without pivoting, and upon triangulation, give A33. So the easiest way I know how to do this by hand is to visually arrange it like this. So you write down your matrix A, and then you augment it with your vector B. And by augmenting, we literally just mean write them next to each other and just separate them by a line. And then we start our EROs. So in this case, what I find easy is to do it similar to the way that we did project 3. I think it was project 3 with Gauss elimination. What you do is you find your multiplier S, to adjust each row after the first one. So obviously we're going to keep 1, 1, 1 because it's already 3 components. And then to find our S vector, so it's easiest to leave that second row alone because it's already only 2 components. We already have a 0 on the left-hand side. So we'll keep that multiplier at 0. We're not going to change it. And then the multiplier for this third row ends up being 2 times row 1. And you subtract 2, 2, 2 from 2, 5, negative 1, because that'll leave you with a 0 here. And then 3 and negative 3. And then from there, you can use your second row to find a multiplier to get rid of this x2 component or y component, however you want to look at it. And that multiplier happens to be 1.5. So you subtract 1.5 times row 2 from this bottom row, and you end up with 0, 0, negative 10.5. And as you're doing all of these EROs, do not forget to do the same thing to your vector B as you do to your matrix A. So our final answer is A33 is negative 10.5. And that you don't actually have to do Gauss elimination, like the full steps. You will have to, like question 4, obviously you have to do, so like with Gauss elimination, obviously you're using it to upper triangulate your matrix, but then you have to back substitute to solve for your vector x. So question 4 here is asking for the x2 component for your solution. So easiest way to do that, plug it in and obviously back substitute. Technically, there's ways that you can use Gauss elimination to lower triangulate and then forward substitute. There we go. So that way, you end up with just one component in the top, 2 in the middle, and 3 in the bottom, and you just do the inverse. It doesn't really matter, but for our sake, it's easier just to do back substitution and upper triangulation. And so simple algebra, really. All you're doing is changing your upper triangulated matrix X and your vector B into your normal systems of equations. So starting with your bottom one, negative 10.5 times x3, because that's the third column, equals 21. Solve for it. Plug in negative 2 for your x3 in your next one. So it would become 2 times x2 plus 5x3 equals negative 4. And you continue on. We only asked for x2, so technically you could stop here, but I finished it out just so you could see. Fifth question is asking for the number of floating point operations. With direct methods, the answer to your floating point operations, or flops, is going to be n cubed, n being the dimension of your square matrix. So in this case, we did a 3 by 3, so n is 3. 3 cubed is 27. Now, problem 1 is pretty easy, pretty straightforward, not bad at all. Problem 2, this is now the iterative methods. This one takes a good bit longer, unfortunately. So let's get into it. Question 1, do you have guarantee of convergence with Jacobi or Gauss-Seidel, given your A and your B? And the way you find that is if your matrix is diagonally dominant, there is a guarantee that it will converge. But if it's not, there is no guarantee. It might still converge, but you don't have any form of, certainty in terms of its convergence. So checking it, as y'all should remember, because we made you write your own octave code to find diagonal dominance. You're checking if the diagonal element is greater than or equal to the sum of the rest of the components in that row. And our first row fails. So, and it's the sum of the absolute value, don't forget that. So in this case, 4 is not greater than or equal to 7 plus 3. Question 2. So given this vector of eigenvalues of, what's the technical name for it? It's like I wish I'd written it down. I want to say it's actually, I guess I could just look it up. Where is it? I was just looking at it. I'm still on problem 1. Sorry, hold on. Here we go. So you're going to be given what we'll call the magnitude of the eigenvalue vector for the iterative matrix T underscore G. That's what this lambda T underscore G is. And so we'll give you A and we'll give you B again. And then give you this eigenvalue vector and ask, do you expect if Gauss-Seidel iteration to converge with this information? So to answer that question, you have to check that all of the eigenvalues are less than 1. So this vector right here, you check to make sure each component is less than 1. If they all are, then yes. If they're not, then no. Simple as that. Then we actually get into the iteration part, which is kind of gross. So with the same vector B in matrix A and an initial guess of 1, 1, 1, then the initial residual will be So in order to find that, remember your residual is equal to your matrix A times vector component X of whatever iteration that you're on minus B. Oh, vector X, I'm sorry, yeah. So in this case, I highly recommend using a calculator. If you have one that can handle things like this, because it's kind of a pain in the butt to actually do all of this and keep track of all of the components. But essentially, what it ends up turning out to be, your residual vector is 2, 0, 12. And then you have to take the infinity norm of that, which is 12, because it's the largest component. And that's it. Looks like I didn't finish this one. So after carrying out one step of Gauss-Seidel, what is your x2? So I found the easiest way to do Gauss-Seidel by hand is to use these equations here. And don't forget, Gauss-Seidel is self-updating. Jacobi is not self-updating. So like here, you solve for x1, your first component of x in your first iteration. That's b1, your first component of b, minus a12 times x2 of the initial guess, minus a13 times the third component of x in the initial guess, divided by a11. So that gives you x of 1 of the first iteration. And then that plugs in down here. So see the self-updating component. So now x2 is equal to b of 2, so your second component of b, minus a21 times that x that you just found, minus a23 times your third component of x from your initial guess. So like, the third component of your initial guess, divided by a22. And we will be giving you a 3 by 3. We wouldn't give you probably anything else because we don't really teach you how to handle anything else. So, it is what it is. Anyway, so our x1 we found is 6 minus negative 3 times 1 minus 7 divided by 4 is 0.5. Now, x of 2 of your first iteration should be 4 minus 0.5, which is 3.5, minus negative 4, so plus 4. That should be 7.5. And that's your final answer. Let's see. I highly recommend, so I published on web courses in the lab resources section, a file that is a review document, and it is extremely comprehensive. I'm going through a lot of what you will be asked on the exam, but not all of it. That review document has everything that you need to know on it. And it doesn't have a lot of extraneous information because you will be asked how to do a lot of things. So I highly recommend taking a look at that because it's extremely helpful. It helped me a lot when I made it, and it continues to stay relevant because I guess it's not been that long. But anyway, you will be asked to do Jacobi iteration too. So we'll say question 5. After carrying out one step of Jacobi, what is x1? So the formula for Jacobi iteration and Gauss-Seidel iteration, as I said before, are extremely similar. The only difference is they're not Jacobi's not self-updating, but Gauss-Seidel is. So I believe just finding your first component of x should actually be identical. Yeah, it should be b sub 1 minus a12 times x2 0 minus a13 x3 0 divided by A11. That's that. Now x2 would be B2 minus A21 x of 0. See, not self-updating on this one. Where did my green go? There it is. Minus A23 x3 of 0 divided by A22. And then x of 3 would be B3 minus A31 x, x sub 1 of 0 minus A32 x3 0 divided by A3 3. Now up here, what the Gauss-Seidel x3 component would look like would be third component of B minus A31 times x sub 1, 1, so your first x sub 1 that you've already found up here, minus A32 times x sub 2 of your first iteration divided by A33. So this x sub 3 utilizes both of the x's that you found before it. Anyway, so technically this value should be the same value that we found before. Let's see, what's another good thing to talk about? We already talked about finding residual. We might ask you to carry out multiple iterations of either Gauss-Seidel or Jacobi. It's easier to do Jacobi because honestly, like with Gauss-Seidel, it gets a little confusing because things update, but with Jacobi, things stay constant because in one iteration, your x's are from the same location. Yeah, let's see. Oh, the equation for finding the number of floating point operations is different with direct methods and iterative methods. So, let's see. I was just looking at that equation. Oh, I passed it. I could have sworn I was just looking at it. Oh, there it is. So, the question would be, say, if it took k equals 5. Gosh, that's hideous. I'm so sorry. K equals 5. Gauss-Seidel iterations. We might make it like way more wordy than this, but it's still going to be asking the same thing. How many flops? Oh wait, I'm sorry, in the order of the number. I'll ask it closer to how we ask you so that you guys don't get confused. Then the order of the number of floating okay. So to find that, the equation is flops is equal to your number of iterations, which is k in this case, times your dimension of your matrix squared. So in this case, it would be 5 times 3 squared, which is 9 times 5 is 45. Ta-da! So pretty easy question. Yeah. So that's about it, I'd say, for problem 2. Now problem 3, where we get into the spicy nonlinear stuff. Given nonlinear system equations, we have our f1 of x1, x2, and our f2 of x1, x2. Let's see. Let's come up with a good one here. 3x1 squared minus 2x2, and then 5x1 squared. Actually, no, we'll leave that. 5x1 plus x2 cubed. Yeah, that looks good, I think. And our initial guess, actually, I'm gonna write this a little differently. Our initial guess, x1, x2 equals 1, 1. So that's going to be the setup to problem 3, and that'll remain constant for all questions asking about problem 3. As you guys have probably gathered from both the last test and how we've been solving the other examples. So do recall all Newton-Raphson, linear or nonlinear, have to have an initial guess. So in this case, we're going to give you 1, 1 as our vector for an initial guess, and your initial guess has to match in size. And so in the case of nonlinear, you have to have the same number of components in your initial guess as there are functions, and that remains constant. For linear, it's just, one's in matrix form, and the other one is in function form. So question 1, we may ask you element J11, 1, 1 of initial Jacobian. So in order to find your Jacobian, I've said this before in my actual class, but I will say it again for the sake of this. What I would do for these problems is symbolically find your Jacobian. So write it out. So your J is equal to, in this case, we'll keep it 2 by 2. It can expand, obviously, to whatever number of functions that you're dealing with. And the number of functions that you have, obviously, corresponds with the number of solutions you have, because you can't have more solutions than you have equations, because then it becomes unsolvable, right? So anyway, component 1 should be the partial derivative of your first function with respect to x sub 1. It's a 1, not a comma. Your second component, your 1, well, yeah, your next component, we'll say on your top row, it's going to be d of 1 with respect to x2. Now, going down, you change your function number. So function 2 with respect to x sub 1, partial of function 2 with respect to x sub 2. Like that. So in our case, the partial derivative of our first function with respect to x sub 1 is 6x sub 1. Partial derivative of our first function with respect to x sub 2 is negative 2. Our partial derivative of our second function with respect to x sub 1 is 5. And our partial of function 2 with respect to x sub 2 is 3x sub 2 squared. Like that. So this Jacobian matrix, we can say it's of K. Holds true for all iterations. But as you change, as you update in your iterations, your values for x1 and x2 will change. And that's when you plug in those values to find them. So to find the initial, we just plug in our guess. So it becomes 6, negative 2, 5, and 3. So we'll ask for J11. Okay, the answer is 6. Ta-da! That's it. Do we ask you? No. So that's good. I was gonna say that we could have put a trick question in there, but I don't think we do, so that's good. Make sure you know how to find residual and convergence for both your initial guess and for up to 2 iterations with nonlinear Newton-Raphson. I don't think we'll ask you for 2. We might. It kind of depends on if they decide to make it spicy on you guys this time. But for now, make sure you at least know how to do 1 of 1 iteration of nonlinear Newton-Raphson and be able to find, the solution vector, your Jacobian for each iteration, and then your residual and convergence, and finding the infinity norm of those vectors. So, anywho, back to what I was doing. So, in this case, let's see, what's a good next question to ask you? Oh, we do ask you for 2, I think. Oof. Anyway, so question 2. After, I know how to spell. After 1 iteration of in L in R, x2 equals, so our formula for x2, remember x is a vector, but it's along the same lines as linear Newton-Raphson. So it's derived from that same formula. However, so k plus 1, so our newest update of x is equal to our old vector x, whatever the one before it was, minus your Jacobian inverse of the previous iteration times the function evaluated at the previous x vector. So this is a very important formula to remember. For some reason, I must have just forgotten that you do have to find inverses of vectors. Finding the inverse of a 2 by 2 isn't like horrible. It's still not very fun. So yeah, that is what it is. Anyway. I'm trying to think of if I should discuss residual and iterative convergence criteria. Because we kind of ask you about it, but it's all really like constant, so well, I guess for now I'll just solve this. So our x of our update, so our first iteration is going to be equal to our initial guess, which I believe, yeah, we set to 1, 1, minus the inverse of our Jacobian matrix from, you know, the initial. So the inverse of 6, -2, 5, and 3. So that answer is unfortunately not super pretty. It comes out to be 3/28, 1/14, -5/28, and 3/14. So I put a detailed way of finding the inverse of a matrix by hand in the outline. There's also another document in the Discord if y'all want to look at it, Funky Fresh Matrices. It's like the name of the document is kind of older, so you might have to scroll up in resources a bit. But yeah, there's a way to do it by hand that stinks. Then there's a way to do it that's not as bad, that's based on Gaussian elimination. So I highly recommend taking a look at those. And YouTube is a helpful resource for this too, because, you know, it's kind of dookie and it takes a while. So yeah, that's the hardest part of this exam. So anyway, yeah, I take a look at those so you can know how I got this inverse. So then we multiply that by this lovely guy here. Oh. Sorry, I got my hand stuck. So our function evaluated at our initial guess, or our two functions evaluated at our initial guess. So that would be 3 minus 2, which is 1, and 5 plus 1, which is 6. Like that. So then that would make our x solution for number 1 turn out to be, let's see, let me do some spicy math real quick. Actually, I guess technically I could use Octave to verify my results. Let's check it out. Project 6, no, project 5 is project 5. So let's see. Oh, how cool. I can re-input my equations. So 3x sub 1 squared minus 2 5x sub 1 plus 6 sub 2 cubed. Which we guess 1. Because I'm lazy and I don't feel like doing all of this matrix multiplication by hand. There we go. goodness. Okay. I was hoping to not have to do this, but I guess we're doing it now. Oh, it's a 2 by 2. Because these fractions suck. We'll likely give you guys like much prettier numbers because I just kind of came up with this one. And I've been using it for like other projects because it's just like easy numbers to work with sometimes, but like in this instance, 0 out of 10 would recommend dealing with these. Oh, God, I messed up. There we go. That. And yeah, I recommend having a calculator that can handle vectors and matrices because that's always like way easier to deal with. One. 1 minus this whole mess. So our solution, nice and pretty fractions. I say pretty sarcastically. 13/28 and -3/28. That's gonna be some not super cute decimal, but like let's see, 3/28 is 0.107 and 13/28 0.4643. So x sub 2 is going to be this ugly little number down here. So yeah, that's it. I think that's as far as I'm going to go today. Do remember iterative convergence for in L and R. We might actually give it to you in the question, but it is x sub I plus 1 minus x sub I and the infinity norm of that. So, you know, it's your newest iteration's x vector minus the previous one's x solution vector, and then the infinity norm of that. And I believe that's pretty much everything. Somebody hopped in the chat to ask a question and then immediately left, so that's cool. Anyway, so yeah, that's everything. Yeah, so good luck on your exam. As I said before, time is going to be the most difficult part. The actual content's not so bad, but actually working everything out is not terribly fun. So be sure to get comfortable with all of these processes. And yeah, good luck. I believe in you.